So after determining the shape functions for this CST element, that is constant strain triangle element, now it is time for us to look at the strain nodal displacement relations for this CST element. And let me remind you that the shape functions which we had seen for CST element, we had seen that shape functions in three different coordinates, that is global coordinates or Cartesian coordinate, then second was local coordinate, and the third was natural coordinate. And the natural coordinate element, the element, this CST element in natural coordinate looked somewhat like this. But now when we'll be looking at the strain displacement relation for this element, we know that the linear strains and the shear strain are defined in this fashion. We usually say that the linear strain in x direction will be partial derivative of u with respect to x. The linear strain in y direction will be the partial derivative of v with respect to y, and the shear strain will be the combination of these two terms, that is partial derivative of u with respect to y plus partial derivative of v with respect to x. Now all this is fine, but what happens is the problem occurs because we prefer to give this displacement function and the coordinates not in terms of this x y coordinate, that is the Cartesian coordinate, but we prefer them in terms of natural coordinates. So we can choose this displacement function. We had seen that the displacement function comes or turns out to be this: u is n1 u1 plus n2 u2 plus n3 u3, and similarly v is n1 v1 plus n2 v2 plus n3 v3, where n1 n2 and n3 are the shape functions of this CST element. And in terms of natural coordinate, this n1 turns out to be xi, n2 turns out to be eta, and n3 turns out to be 1 minus xi minus eta, which we had seen in detail in our last video. And then if I substitute this values of n1 n2 and n3 in this equation, I will get this displacement function u and v as this. Just if I substitute this n1 as xi, n2 as eta, and n3 as 1 minus xi minus eta, and if I just rearrange them, I will get this u and v as this. So now here we see that this displacement function u and v are no more in terms of the Cartesian coordinate, but they are in terms of the natural coordinates. And then similarly, if I want to find these coordinates in terms of the nodal coordinates, again what I can do is, if I'm using now the same shape function to determine the coordinate in terms of nodal coordinate, then those kind of representations are called as isoparametric representation. Now this isoparametric representation means, again the isoparametric representation means that if the shape functions which are used to determine the displacements is are the same as that of the shape functions of shape functions used in that of coordinates, then those kind of representation or those kind of formulations are called as isoparametric formulation. Here we can observe that the displacements were determined by these shape functions n1 n2 n3 and n1 n2 n3, and even these coordinates will be determined by using this same shape functions n1 n2 n3 and n1 n2 n3. Now because of this, they are called as isoparametric representation. And then if I just substitute this values of n1 n2 and n3 the way we had done here, again in this for these coordinates, we will get these coordinates as this. Now if I use this property that xij, if I am denoting this as xi minus xj, then if I use this property, I can represent this coordinate function as x is equal to x13 xi plus x23 eta plus x3, and I can represent this y as y13 xi plus y23 eta plus y3. What I have done is I have just made this y1 minus y3 as y13, and I have just denoted this y2 minus y3 as y23, and same thing with x1 and x3. So now basically what we can observe from here is this u and v are not only the function of x and y, but in turn they are the function, this u and v and x and y, now they are the function of xi and eta, which are nothing but the natural coordinates. And we had seen that the moment we switch the coordinates from Cartesian to natural coordinate, it becomes all the calculations becomes very simple. It simplifies our process to a large extent, and that is why we choose to represent these displacement functions and these coordinate functions in terms of natural coordinate. But now the problem will happen when we will try to use this, when we will try to use these functions in this expression, that is to find epsilon x, epsilon y and gamma xy, because here this functions, we take the partial derivative with respect to x and y, but here now we have the coordinates as xi and eta. And because of this, what we'll have to do is, but one before that, one thing we need to understand, that u will be now the function of x, which will be function of xi and eta, and then it will be a function of y, which will be again the function of xi and eta. And similarly, same thing happens with v will be function of x, which will be in turn the function of xi and eta, and similarly y will be function of xi and eta. Now because of this, what we'll have to do is, if at all, if I want to find what is dou u by dou x in order to determine epsilon x, or if I want to find what is dou v by dou y to determine epsilon y, or the other combinations to determine gamma xy, I will have to take the I will have to take the partial derivative of this u and v with respect to xi and eta by using something called as chain rule. That is, if at all, if I want to take the partial derivative of this u with respect to xi, then I can take this as dou u by dou x multiplied by dou x by dou xi, plus it will be dou u by dou y multiplied by dou y by dou xi. This is nothing but this is the chain rule. And similarly, if I take the partial derivative of this u with respect to eta, I will get this as dou u by dou x multiplied by dou x by dou eta, plus dou u by dou y multiplied by dou y by dou eta. Now this I can represent in terms of matrix as this. So I can club this dou u by dou xi and dou u by dou eta together, and this terms dou x by dou xi, dou y by dou xi, dou x by dou eta, dou y by dou eta together, and then I can bring this out, dou u by dou x and dou u by dou y. Now basically, if I want to determine what is epsilon x is nothing but dou u by dou x, so I will get it from here. So somehow I will have to take the inverse of this matrix, and then if I multiply it with this matrix, I will get dou u by dou x. Similarly, if I take the partial derivative of this function v with respect to xi and eta, and then if I similarly frame this kind of matrix, I will get here dou v by dou y, and again if I take the inverse of this matrix, I will I will get what is dou v by dou y. But now for this, let us look at this matrix for a time being. This matrix is a very important matrix, and it is called as a Jacobian matrix. This matrix is called as a Jacobian matrix. Now, what Jacobian matrix does is, this Jacobian matrix can be defined as a transformation matrix. It is a transformation matrix used to transform the values of displacements in natural coordinates to the Cartesian coordinate. So this matrix will help us to switch or to transform the values of the displacement from this natural coordinate to the Cartesian coordinate, and that is what we want to determine this strains in x, y, and in shear direction. So what we'll do is, I will denote this matrix, Jacobian matrix, as J. And then further, if I want to find what is dou u by dou x or what is dou u by dou y, and then what I will have to do is I will have to take this matrix that side. That means basically that will be the inverse of this J matrix. Now if I want to find this J matrix will be nothing but, here the first term in the J matrix is dou x by dou eta, dou x by dou x by dou xi. So basically I will have to differentiate this x with respect to xi, and if I do that, if I differentiate if I take the partial derivative of this x with respect to xi, all this term will be treated as constant, and I will get this term as x13. So basically I get this term as x13. Now similarly, if I find what is dou y by dou xi, then dou y by dou xi will be y13. So this will be y13. And then similarly, if I find what is dou x by dou x by dou eta, then it will be dou x by dou eta will be x23. So this will be x23. And then similarly, if I find what is dou y by dou eta, what is this term, this dou y by dou eta, it will be y23, and therefore I get this Jacobian matrix as x13 y13, and this will be x23 and this will be y23. So this gives me the J matrix or the Jacobian matrix for this triangular element, that is CST element. But here if I want to find what is dou u by dou x or what is dou u by dou y, I need to find the inverse of this J matrix. And if you know the procedure to find the inverse of 2 by 2 matrix, it is very simple. This will be 1 by determinant of J multiplied by the matrix will be this will become y23, this term will go there and this term will come here, this will be x13, and this term will remain as it is but with now negative sign, and this will be minus x23. So this will be the J inverse. Now if I substitute this J inverse in this equation, I will get that as this dou u by dou x, dou u by dou y is equal to 1 by determinant of J times y23 minus y13, this entire matrix, times u1 minus u3 and u2 minus u3. Now this value dou u by dou xi and dou u by dou eta turns out to be this. This is nothing but dou u by dou xi will be nothing but, we have here the expression for u. U is this expression. Now if I take the partial derivative of this u with respect to xi, this term will be treated as constant and they will become 0. So I will get dou u by dou xi as u1 minus u3. So that is what has been written here. This dou u by dou xi will be u1 minus u3. That is what has been already written here. And then similarly dou u by dou eta will be nothing but dou u by dou eta will be nothing but v2 minus v3. Dou u by dou eta will be nothing but dou u by dou eta will be nothing but u2 minus u3. So dou u by dou eta will be u2 minus u3. So in place of this J inverse we will write this matrix, and in place of this term dou u by dou xi and dou u by dou eta we will write this matrix, and finally we will get this equation. Now further I will just multiply this 2 by 2 matrix with that of 2 by 1 matrix, and I will get that as 2 by 1 row, 2 by 1 column vector. So this will be nothing but this term multiplied by this term. So it will be y23 multiplied by this term minus y13 multiplied by this term, and then similarly it will be minus x23 multiplied by this term plus x13 multiplied by this term. So finally here I get this dou u by dou x and dou u by dou y as this term, right? So from here I can directly now evaluate what is epsilon x, or epsilon x is nothing but dou u by dou x, and that I will get as 1 by determinant of J times this term, right? Then this dou u by dou x will be this term, and then dou u by dou y will be this term. Of course, again this 1 by determinant of j will be there. So epsilon x, basically I get that as dou u by dou x is equal to 1 by determinant of j times all these terms. So basically what has been done here is this has been multiplied now. Y23 is multiplied by u1 minus y23 is multiplied by u3 minus y13 is multiplied by u2, and then again this y13 is multiplied by this u3, and then further what I can do is I can just rearrange this term. I have written this term here first, and then the u2 term I have written it here, and then this u3 terms I have combined, so it comes to y13 minus y23 times u3. And then if I just do some readjustment, that is minus y13, I can write this y13 as minus of this sign minus of y13 is nothing but y1 minus y3. And then if I just take this minus sign inside, it will give me y3 minus y1, and then further I can write this again as y3 1. So basically minus y13 turns out to be y3 1. And similarly, if I just try to evaluate this y13 minus y23, that will be nothing but y1 minus y3 minus y2 minus y3, which will result in cancellation of this y3 terms. So I will basically get this as y1 minus y2, which will be again y12. So basically this epsilon x, now I get it as 1 by determinant of j y23 u1 plus y31 u2 plus y13 u3. So this is nothing but the strain displacement relation, but this displacement is in terms of the nodal displacement. So finally I have been able to evaluate what is epsilon x. So epsilon x in terms of nodal displacement, we get it as this. Now I need to find what is epsilon y and what is gamma xy. To find epsilon y, I need dou v by dou y, right? And to find gamma xy, I need dou u by dou y plus dou v by dou x. So to find this gamma xy, I have already found this term dou u by dou y from here, right? Now in the process of finding this epsilon y as dou v by dou y, I will get also the second term as this. So finally I will add this term with this dou v by dou x, and I will also get gamma xy. So now let us see how to find epsilon y. The way we had got this matrix, by taking the inverse of this Jacobian, I had managed to get this matrix. Similarly, I can obtain this matrix for the v term as v term as this. This will be my matrix for v term. So from here again I can very easily write epsilon y as dou v by dou y, which I know, and that will give me this matrix, that will give me this equation, that is dou v by dou y will be equal to 1 by determinant of j, this term, this sorry, I want this term, I want dou v by dou y, right? I want dou v by dou y. So that will be nothing but dou v by dou y will be equal to 1 by determinant of j, and then this multiplied by this, so that will be minus x23 multiplied by v1 minus v3 plus x13 multiplied by v2 minus v3. So finally again if I just do those rearrangements, that is minus of x23 will be nothing but minus of x2 minus x3, this will be nothing but x3 minus x2, and I can write this as x32. So if I do that, and again if I do some other changes, I can easily write this epsilon y as this. Now here in the process of finding epsilon y, we have also got this term now, dou v by dou x, right? We have got this term, and this term we had obtained it earlier. Now if I just substitute what is dou u by dou y and dou v by dou x, I will get gamma xy as this term. Now finally we have been able to obtain all the three strain terms, that is the for a two-dimensional case we will have the three strain terms, that is epsilon x, epsilon y, and this should be gamma xy. So we had got this epsilon x as 1 by determinant of j y23 times u1 plus y31 times u2 plus y12 times u3, right? If I multiply this with this, I will again get back my epsilon x expression. Similarly, epsilon y, just now we got it as x32 times v1, right? So x32 times v1, because this u1 will be multiplied with 0 and that will become 0. So finally I will get it as x32 times v1 plus x13 times v2 plus x21 times v3. So finally I will get back this equation, and then similarly if I multiply all this with this, I will get the expression of gamma xy. So this is a very important matrix which is called as the strain displacement matrix, and it is this matrix, this entire matrix is denoted by B, and it is called as strain displacement strain displacement matrix. And this, again, let me remind you that this displacement will be in terms of nodal displacement, so it is also called as strain nodal displacement matrix. Now this is the matrix which will help us to determine the strain in the 2D CST element, provided by somehow, that is by using finite element method. If we can successfully determine this nodal displacement at the three nodes, that is node 1, node 2 and node 3 in CST element, if we can determine this displacement at this three node, then by using this strain displacement matrix I can easily find the strains that are developed in the CST element. And then further, if I know these strains, the three component of the strain, I can very well use this matrix later on, that is sigma is equal to d times epsilon, where d is the matrix which will relate stresses with strain. So once we had already seen this D matrix for the plane stress case and plane strain case. So finally, if I want to find the stresses, what I can do is I will have this D matrix, and then this epsilon will be nothing but B times Q. So finally, this will be the matrix which will help us to determine the stresses in the CST element.